Hey everyone, welcome to your notes on separation methods. Your standards from the state of Georgia are posted at the top. Your learning target that the district and I would like for you to be able to do is to construct an argument from the evidence using principles of intra and intermolecular forces to determine the identity of substances based on their chemical and physical properties. And we'll be working on this more in class too, but these notes are some of the background information for that. Why would you even want to do this? Well, so when I was a student in chemistry, both in high school and in college, I honestly had no idea how to separate things. What I mean is say you have an unknown substance at a crime scene. How does the crime scene investigators figure out everything that's inside of it? I didn't learn that till I was a senior in college and took chromatography. And so chemistry just always seemed like this magical voodoo thing that all of a sudden everything could be separated. So I hope that you guys don't feel the way by the end of this. So I want you guys to be able to understand how chemists and crime scene investigators figure out what's inside something unknown. Your success criteria: I'll know I've got it when I've identified a substance based on its physical properties. I'll know I've got it when I've explained the phenomenon like dissolves like in terms of intermolecular forces, and I'll know I've got it when I've described how various separation methods work. All right, so let's just talk about identifying a substance based on its physical properties. So first of all, remember that there are extensive physical properties like mass or volume. So that's based on how much of something there is. And those aren't usually helpful to identify something because you could just get more of it or less of it. But the intensive physical properties that we talked about last time are ways that we can help identify our substances. And also, you might not have ever learned this, but there's very few things that have one single test that will definitely identify something. So usually chemists do bunches of tests and then they use all that data to make the argument that we think it's this. Here is some data on, there's an unknown substance, and then you look up in a reference manual and you find compound A has those melting points and compound B has those melting points. Again, you look up magnetism and color and density, and you have your unknown, and you're like, oh, okay, so here's my numbers. I am going to claim that the compound might be A, but I know it's not B. So how would you do your evidence and your justification or your reasoning for this? So both compound A and the unknown are magnetic, green, and have densities near 0.79 grams per milliliter, similar melting points. Compound B has the same melting point, but different magnetism, color, and density. So the justification, remember, we bring in scientific principles here to explain the evidence and support our claim. So identical compounds have the same intensive physical properties, so the unknown could not be B. Intensive physical properties alone are usually not enough to confirm the identity of a compound, so further investigation would need to be done to confirm that the unknown is A, since so many of its properties match. Unless we knew ahead of time, like a teacher said, well, look, it might be this or this, choose which one it is, then we would be able to say that the unknown is A. But if we were just out of the blue, trying to figure out what unknown was, and we looked up some data and we found oh, well, compound A, whatever it is, sodium chloride, it's probably sodium chloride because it matches melting point, that wouldn't be enough. This is could be a poster or just an overall diagram of a whole bunch of separation methods that we will talk about throughout the year. We're not going to talk about them all today. But again, if we want to analyze something and see what's in it, first of all, we have to break it into its components. We have to purify it. And so there's many, 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 many ways that a chemist can purify things. And these are some of the ways. We'll talk about several of them today. So one of your separation methods, super simple, magnetic attraction. And so you could grind up something ore is from mines and stuff, like the way what we get metals out of and other minerals. And so if we're trying to get a magnetic metal out of it, like iron, we could just grind up the rock and put a magnet by it, and the pieces of iron will hopefully come out. Other methods for things that are not soluble, that means they don't dissolve, we're going to separate them by particle size and by gravity. So a sieve is just like a strainer or a colander, and you can use bigger sieves and then go smaller and smaller, so first the big pieces come out, then the medium size, then the smaller. Or filtration. You've probably filtered many things in the past. And so this is when you have filter paper or like a coffee filter or something like that. And so if you had something that didn't dissolve very well, you could pour it through and only the liquid would come out. And then there's something called sedimentation and decantation. Basically, you just let it sit for a while and like all the sediment falls to the bottom, and then you carefully just pour off the liquid on top, and then you don't really need a filter paper. A centrifuge is a really cool device, and this is again for things that aren't truly dissolved but suspensions, like things that you think are liquid, like milk or blood or things like that. They look like liquid, but they actually have a lot of things just floating around in them that aren't truly dissolved. So a centrifuge puts like liquid in tubes, and then it spins around and around and around really fast. And so substances with the highest density go to the bottom by centrifugal force. And so the lowest density substances end up at the top. And one example of when this is done every day is when blood needs to be analyzed or blood donated. The blood is spun down, and so the plasma ends up on top and the blood cells end up on the bottom. Fractional distillation is a method that separates liquids based on their boiling points. And remember, we're trying to tie in intermolecular forces here to this. And so stronger intermolecular forces hold the molecules together, so they're going to take more heat at a higher temperature to pull apart into liquids or gases. And so stronger intermolecular forces have higher boiling points and higher melting points. So what do we do? If you look at the diagram on the left, you have liquid in the flask on the left, and it's boiled. And then the vapor will come up across, and as the diagonal tube comes down, there's cold water in that tube. So the cold water condenses the vapor, and then it turns back into liquid, and then the little flask on the right, the receiving flask, collects the liquid. Now, what happens is if you have a mixture of liquids with different boiling points, the one with the lower boiling point will actually boil first, and the one that has the higher boiling point will stay in the boiling flask because it won't boil at that temperature. And so the first one comes off, and then if there's a whole bunch more liquids, then the next one, and then the next one. So one thing that this is useful for is alcohol. So alcohol like vodka, if you have like 42 proof or 151 or 80 proof, like that's obtained by boiling off a certain amount of alcohol, and the alcohol boils off first, and then the water is held into the boiling flask, and that wouldn't boil off until the temperature got higher. And another one is petroleum, so gasoline. So crude oil is like a mixture of a whole bunch of different things. And so the furnace on the right shows how it would heat it to really, really high temperatures. And then the column on the left is like cooled in steps. So like the bottom part is like at 400 degrees Celsius, and that's when like lubricating oil and paraffin comes off. Then it lets the gas go up further, and then the next one's cooled to 370, and that's when fuel oil comes off. And then the next one is at 300, and that's when diesel, and then kerosene, and then gasoline. So that's how crude oil is separated in a refinery. One of the main things I want you to get out of learning about intermolecular forces is a principle called like dissolves like. Okay, so this is super important. And what this means is, like, we learned about nonpolar and polar molecules and London dispersion forces and dipole-dipole and hydrogen bonding. So nonpolar molecules only have London dispersion forces. Polar molecules have London dispersion forces and dipole-dipole, and hydrogen bonding if they have HN, HF, or HO groups that can be hydrogen bond donors and acceptors. So what happens is polar molecules have all these forces, and so if there's like a polar molecule around and a nonpolar molecule around, the polar is going to attract the polar, right? It's not going to interact with the nonpolar because it doesn't have a reason to. It doesn't have forces pulling it together as strongly. So if you have like a mixture of a polar liquid and a nonpolar liquid, generally they separate like oil and water. And so now imagine you're trying to dissolve something in it. Well, if you're dissolving, say, salt, which is ionic, it's going to go to the polar liquid because it has like stronger attraction with that liquid than it would have with the nonpolar liquid. Versus a nonpolar solute, if it tries to go to the polar liquid is just going to be like, no, I would rather bond with my neighbors, other polar liquids. I'm not going to try to bond with you, nonpolar solute, so you can just hang out in the nonpolar liquid. So we can see this everyday life versus with like oil and vinegar salad dressing. So you can shake it and shake it, but eventually it separates. If you put salt in, it would go to the vinegar layer because that would be the polar layer. It wouldn't go to the oil layer. So we can use this in the chemistry lab with something called a separatory funnel. And so what you do is you put two solvents in the separatory funnel, and so if you had like a mixture of solute, maybe it was nonpolar, maybe it was polar, or maybe you had both. If you shook it, then the nonpolar solute would go to the nonpolar solvent, and the polar solute or the ionic solute would go to the polar solvent, and then you just let it separate, and then you can drain it off on the bottom. So you drain off whichever one is on the bottom first, and then you're left with the other layer on the top by itself. One thing I also wanted to just note is that there is another reason that like dissolves like, and that's because of entropy, and we will talk about that a little bit more when we get to entropy. Chromatography is probably the most important method in all of chemistry for separating things. It is for any analytical chemist or any drug company or things like that, chromatography is like the go-to. And it uses the principle of like dissolves like. And I just want to give you two analogies first so you can kind of see what's happening here. So the first analogy is, imagine you have a mixture of bees and hornets, okay, over flowers. And so hornets don't really love flowers, but bees, do love flowers. All right, so they're swarming, the wind is blowing, and they're going. So all of a sudden they're going to see these flowers, and the bees are going to stop and like pollinate and get some nectar, and the hornets are going to keep going. So the hornets will leave the bed first. Eventually the bees will leave once they've done their thing, and so the bees will come out second. Another analogy would be like a flowing river. Okay, so if you had leaves and heavy stones, then leaves would be carried much further and much faster down the riverbed than heavy stones would be. Eventually heavy stones would probably come down by erosion, but the leaves would definitely come down first. Chromatography uses those same principles, or the analogy will hold. This is your notes. I'm going to go to the next slide where we just focus on the pictures, and we'll talk about what's in the text of the notes. Maybe in elementary school or middle school, you did paper chromatography where you took like a black pen and dissolved it maybe in alcohol and then put a paper towel there or a coffee filter and saw the dyes separate. Or maybe you did it with grinding up plant leaves and saw the plant pigments separate, which was actually the first way that chromatography was discovered. So in the chemistry lab, most chemists don't necessarily like paper towels, but it follows a similar process. So they use something called a thin layer chromatography plate, and it's like a paper towel, but it has something called silica gel on it, and that is a polar substance. So the process is you put little spots of either known things or unknown things, like at the very bottom of the paper or the plate, and you might need to dissolve it in a little bit of solvent and then put it on there and let the solvent dry so it has like a spot at the bottom. And then you have a mixture of two solvents, a polar solvent and a non-polar solvent. And what you do is you just have a tiny little bit at the bottom of a beaker or a glass or something, and you put the edge of the paper or the TLC plate in there. And so as you can see on the left, what happens is the solvent starts going up to the top. And this is by capillary action, which we talked about before. So remember, capillary action is like a combination of adhesive forces where the solvent molecules are grabbing onto the walls of the TLC plate or the paper towel, and cohesive forces where they're holding onto each other. So they're kind of just clawing over each other to get to the top. That's capillary action. And so what happens is if you have a nonpolar solvent and a polar solvent, if you look at the middle picture, you'll see that the polar solvent will want to be attracted to the polar paper or the polar TLC plate. And so it'll kind of hang on more, where the nonpolar solvent is like, no, I'm not, well, really the paper is like, I'm not going to bond with the nonpolar solvent because like dissolves like. So the nonpolar solvent goes much further to the top much faster. And so if you have a mixture of polar and nonpolar solutes dissolved, spotted on the paper, they will dissolve in the liquid as it goes up. And so again, the polar solutes will dissolve more in the polar solvent, and so they will take much longer to go up, whereas the nonpolar solutes will dissolve in the nonpolar solvent and won't be attracted to the paper towel or the TLC plate, and so they will go up further. And basically, that's how you can separate out different components. Like if you did the marker on the paper, you separated out the different color dyes because they had different polarities. And you can also use this to identify things. So on the right is actually a picture I took when I was in chromatography as a college student. And so the 1, 2, 3, 4, 5 lanes on the left are pure substances. Like I knew what these things were. And then the 1, 2, 3, 4 lanes on the right were things I did not know what they were. And they were mixtures. And so I was able to identify what was in the mixtures by comparing how far the spots moved to the known substances. So for example, the one with the purple circles around it, so the two of the mixtures had that compound in it. One of the mixtures had the compound with the blue circle in it. One of the mixtures had a compound with the red circle in it. One of the mixtures had a compound with the orange circle in it. So to do this for identification, you have to have a known and then you have your unknown, and maybe you want to confirm that your unknown is that. Well, if it moves the same distance as the known, then it adds evidence that it might be that. For example, we tried to synthesize a dye in the lab, and so like we had a purified dye that we bought from a chemical manufacturer, and then we had the one that we made, and so we put it on the plate and looked to see if it went to the same distance, and it did. And so that was one of the pieces of evidence we used to argue that we had successfully synthesized the dye. The other thing that is useful for the chromatography plate is maybe you think that you've synthesized something pure, and this happened to us too when we were making this dye. So we thought we made pure dye, but then it moved and there was like 2 or 3 spots, and we were like, oh, wow, there's side products, there's extra things that we're going to have to purify out of this dye. So that's another use for chromatography. Column chromatography and HPLC are like bigger, larger volume examples. And again, I'm going to go to the next slide that focuses just on the pictures, and you can read along with the text in your notes. Column chromatography is like a big glass tube or a column filled with packing material that could be either polar or nonpolar. And what happens that you do, or the way that you use it, is that you put your sample on the top, and it might be a mixture of things. And then again, just like the paper chromatography or the thin layer chromatography, the TLC plate, you put it in a mixture of polar and nonpolar solvents. Well, here we just pour a mixture of polar and nonpolar solvents in. And so imagine that the packing material is polar, like silica gel, so the nonpolar solvent will come through faster, and it will take the more nonpolar substances through first. And so in this picture you could see that the red came out first, okay, and then the blue, and then the black. And so that's, if you have like a bunch of material, that's one way that you can separate it out. And so the picture on the right is that dye I was talking about that we made in the chemistry lab. And so we put it at the top, and then there was like a pink contaminant that came out first. You can see near the bottom, pink is coming out, and then like a bluish green dye came out later, and that was what we had tried to make. So HPLC, high performance liquid chromatography, takes us to a whole nother level, because this process takes forever, like pouring in the liquid and letting gravity push it down. So instead, what is usually done in most labs, like, or in the crime lab or things like that, is a machine pushes the liquid through the column at like super, super, super high pressure. So this process happens much faster. The last form of chromatography we'll talk about is gas chromatography. And again, this uses the same principles, and this is extensively used in labs where they try to identify things like crime labs. So instead of liquid going through, though, a gas flows, a gas that's not going to react with the things, so usually a noble gas, and it's usually a nonpolar gas as well, like helium. So you have your mixture of things and you heat it really high so the mixture vaporizes. So if it was a mixture of liquids, like you heat it and so the liquids will vaporize, and then the gas, the helium, flows through the column and pulls those the vaporized gas with it. And so again, the same thing will happen as far as different substances will come out first based on polarity, boiling point, attraction. This is a little more complicated about the things that cause which substance to come out first than maybe just the column chromatography or the HPLC or even paper. But yeah, so there's several things, but basically this is one way that you can separate them out. After they come out, then you can use analytic techniques to figure out what they are. Here's just a super quick animation to show this happening. And so while you're watching it, imagine that the packing material, the stationary phase is called, is polar, and that the red materials would be nonpolar, so they would come out first. Then the blue materials would be very polar, and then the yellow material would be somewhere in the middle. Thank you to Canal Divulgación for making this awesome animation. So how'd you do with the Edpuzzle questions, and how do you feel like your understanding is? Do you feel like you've met the success criteria and can do the learning target? I hope that you can. If not, please try watching the video again or ask me if you have any questions. If not, we will see you in class and at the next video.